Aleksei is a PhD candidate at Colorado School of Mines in the Reservoir Characterization Project, Department of Geophysics. Aleksei got his master's from St. Petersburg University and is a geophysicist in Colorado School of Mines. He's been working on laboratory and flow loop DAS experiments. And so, Aleksei, please take it away.
Thank you, Nate. So today I'd like to discuss some laboratory and flow loop dust experiments. So here I have this logo. Actually, I created this logo. It's our fiber optics research program. It's a joint effort between petroleum and geophysics department. So we're trying to develop some mostly oil and gas applications for distributed acoustic sensing. And today I would like to talk about laboratory and flow loop dust experiments. Partially, it will be regarding my work in Lawrence Berkeley lab, where I was intern for a couple summers, and partially it's a chapter of my PhD thesis. So the outline of my talk today will start with linear fiber stretcher experiments. So this is what I did in Berkeley lab. So I will cover something on dust response, spatial resolution, temperature response, and dynamic range, and also come with some quick conclusions regarding this part of my talk. On flow loop experiment side, I will show you some of our results, which we are receiving at FORP. And there will be some established algorithms which use now in industry, something like Doppler effect and eddy tracking. And also I will cover something what we develop in it, thermal-based slug flow monitoring. And I guess my last slide will be more like for discussion. And the idea of this talk, I guess, to show you that DAS is more than seismometer array, and you can apply it in different things. So linear fiber stretcher experiments, there was a couple of talks on that. One of them was during AGU. My co-author is Nate Lindsey and Jonathan Franklin. Also, I would like to acknowledge all my colleagues in Berkeley lab, Eileen Martin for some nice suggestion, and my advisor, Godrin at Colorado School of Mines. So what the motivation of this project was to build some linear fiber stretcher which can handle some of the field cables. So usual approach, as you can find in the CFOAM documents, which I put into the Slack, that we usually used special piezoceramic stretchers to calibrate our DAS instruments, but it can handle only bare fiber. And for those who do not know, I have here what we call pigtail. You can zoom in video a bit. And the bare fiber, it's very, very small portion. It's like 120 microns. You barely can see it on the tip of this fiber cable. And after that, you have a buffer, what we call primarily protected fiber. And you know that managing only this very small fiber, it's not the best option for if we want to test the tool in kind of more field cables. So we decided to build this linear stretcher. It's more than gauge length in length, so it's 11 meters. Our gauge length is 10 meters. We can adjust it so it's directly straight. Other components, we use a fiberglass pipe to support our cable. We use pretty precise actuator, so it can manage the strain steps of 3 nanostrains, which is very small. It's an optical installation, basically this accelerometer and all other pieces. So we try to achieve precision there. And regarding the tool which we use to record our data, we use Silixi DAS from Berkeley lab. It has 10-meter gauge length, 25-centimeter step. And here you need to pay attention that this is not our spatial resolution, just our sampling. And to validate our results, we use Luna optical frequency domain reflectometry tool. And just to clarify what is it, it's a very precise tool. It can measure real strain values with about 2 millimeter resolution, but it's limited in length. You can use it only for about 50 meters to require your strain data. And we tested different cables in this experiment. So the experiment is basically to strain the cable and to see how our DAS's response to our strain, to induce strain in the cable. So here on the left, I have in this blue and a bit spiky, it's a real strain distribution, which is received using this optical frequency domain reflectometer. So you can treat it as a real strain which is applied in the cable. After that, we decided to understand how DAS response should like. So the first step is our convolution with gauge length. So you can treat it as a moving average filter. And this is our orange curve. The next thing, Felix also applied some moving average on the fly. So we applied this moving average as well. And we received this yellow curve. But you see that it's still not the same as our magenta curve. The special distribution is quite the same. You see, if you will closely see into these corners, you see that the orange and magenta lines, they kind of the same distance, correspond to the same distance, but the amplitude is different. And that's also what we probably see in Veronica's work, where we have some mismatch between DSS and DAS. So there could be some different explanation to that. It could be calibration of the system. And another thing, if we pre-strain our fiber first, it could deform slightly our waveguide, and it also could cause some different in our strain measurements. Other things, we induce the periodical oscillation in our strain and basically support the findings from Matt Becker experiment, what Nate presented. So it remains flat, and we have 20 to 30% difference between our real applied strain and the strain recorded by DAS. The next thing is a spatial resolution, and I guess Matt Becker mentioned it during his lightning talk. So we need to understand that DAS doesn't measure the exact strain. So here what we did, we induced a very small strain in some limited number of limited distance along the channel, along the cable. So we have about 20 centimeter spikes of strain, and they separated with different length from 2 to 25 meters. So this is our DAS data. So you see when we starting to separate our spikes, we finally can resolve that we have 2 spikes. But to understand it in a more precise way, this is the 3 different distributions recorded with our OFIDER system. You again can treat it as a real strain. So here we have 2 meter, 11 meters, and 25 meters difference between these spikes. And this is our DAS response. So 2 things to mention. The first thing, that if we have spikes close together, we can resolve them. And another thing, if we apply, for example, 100 microstrains, it's our real spike, we record only 1 microstrain in DAS. And it makes sense because we average over gauge length and apply some additional moving average filters. So we see here that the 2 responses totally separate when we have more than 2 gauge length separation between 2 spikes. So that's something you need to pay attention, that DAS doesn't measure real strain distribution, and multiple strain distribution can lead to the same DAS response. Another thing we found, we just was checking our temperature response. So we put a bare fiber to some water circulatory bath, which has a precise temperature control. We heat it up, and after that let cool it down for several hours. And we noticed that the DAS response, this is response from the DAS, and this portion of the cable was located in this bath. It's pretty similar. A few things to notice, that when we're heating it up, it took less strain when it's cooling down. And here we are coming to dynamic range issue. But besides that, we estimate this thermal expansion coefficient, but it's not thermal expansion coefficient for the pure silica glass. It's more like combination of this one and other thermal expansion coefficients. For example, if fiber is lying onto some metal plate, it will also influence our results, and basically thermal expansion coefficient of this plate. On dynamic range, it's quite interesting. So what we're doing here, we apply the same amount of strain. It's about 30 microstrains what we recorded with DAS. and we apply it with different strain rate. So initially we strain it very slowly. After that, we start to strain it very fast. So the strain rates vary from 4 to almost 500 microstrains per second. And we're recording the same procedure of straining the cable with different sampling rates from 500 Hertz up to 10 kilohertz. And I should say that only 10 kilohertz sampling resolve all these signals properly. With sampling which is less, like 500 Hertz or 2 kilohertz, we have some issues. For example, the 9 microstrain per second can be resolved with all frequency sampling rate perfectly, but after that, for example, 18 microstrain per second, 500 Hertz sampling rate does not resolve it properly, and we start losing the signal. The same occurs with our 2 kilohertz sampling. So what's the issue here? We are measuring optical phase, which changes from -pi to pi, and as the our phase increase more than pi, it means that we skip this cycle and just moving from -pi to pi. And after that, we need to apply an unwrapping algorithm to properly restore our phase. And if we just apply the equation, which Nate already talked about from Hartek book, and just substitute the values, we will receive this limitation of 35 nanostrains. And this limitation is 35 nanostrains per time sample. So if we have a larger sampling rate, we increase our dynamic range, total dynamic range, and also we can play with gauge length. If we have a smaller gauge length, it also could influence our dynamic range. And this is something you need to pay attention for some applications. It's where we have large values of strain rates. It could be anything from very close earthquake, which propagates in line with your fiber direction, or it could be some oil and gas applications when we're recording some perforation noise or perforation shots or fluid or slurry, which is going through perforations. And I guess we will expand a bit on that, and there should be a sensors paper on that soon. So there are some observation. So we found that the strain values are less than applied when we recorded with DAS, and there could be some explanation to that. And it's probably explained partially what Veronica mentioned in her talk. Also, we found the temperature, or I should say, we just check that temperature variations also is hardly influence our DAS data, and we need to take it into account. We estimate this upper limit for DAS system, and I believe there could be some improvement on that if you use 2D unwrapping algorithms, but it's mostly like the upper limit, so you can do anything with that on hardware side. And also we showed again that we can record very broadband signals, and it's very sensitive to temperature, so you should not treat DAS only like acoustic sensor, but also as a strain measurement approach for some geodetic process and some temperature sensor. Next, let's shifting gears to some fun stuff on flow loop side. And this is mostly targeting oil and gas industry, but you can apply the same things to basically any research you might have in mind. Here I have my co-authors from Colorado School of Mines, and we presented in a couple workshops, and they're coming presentation site of petroleum engineering meeting. And also I would like to acknowledge some undergraduate students who help us with the experiment, and our collaborators from OptaSense. So with this experiment, we are trying to understand how we can use DAS to extract production log, or just to understand what's production log. We want to understand, if you have a horizontal wellbore, which zone produce what? Is it water, oil, or gas, and how much it produces? So we mimic firstly in this vertical flow loop experiment. The main part is our vertical pipe, and we, because we have only limited space here, we wrapped the fiber around the pipe so we can have more data samples here. and we're wrapping it with roughly 1 centimeter step. So you can treat effective gauge length here is about 1 meter. And what we're doing here, we flow in different types of fluids. It could be water or air or mixture. And for some experiment, we add in some additional very small amount of warm water, and I will comment on that a little bit further. But first, I would like to share some common approaches, and we validate them in these lab experiments. So one of the approaches, which was firstly published by Shell and Silixa, we can use Doppler effect. It means that the wave, sound wave or tube wave, which propagates with direction of the flow and against direction of the flow, has different velocities. And we can extract these slopes. This is our FK domain. You're familiar with that from our notebook experience, Jupyter notebook experience. So you can extract the slope, and it will provide you with velocities, and after that you can sum it and divide by 2. It will be speed of sound, and you can just basically subtract it, and you will receive a flow velocity. So that's how you can receive 30 meters per second, which is very close to the flow velocity measured by flow meter. Another approach is to monitor for eddies at some small whirlpools, which could occur in the flow. And here we need to zoom in into like lower frequency range. And in this low frequency now you have only one-sided propagation, because whirlpools, they propagate only with direction of the flow. And again, for some types of flow, it's provided with pretty nice estimation of flow velocity. And the last part of this flow loop experiments consists of some slug flow experiments. Slug flow is very common in our oil and gas industry, and could initiate some damage to the equipment. So it's a hot topic now, how we can monitor this slug flow. Slug flow consists of gas phase in shape of Taylor bubble, and after that you have some smaller bubbles submerged into this liquid slug. So that's how it looks. And we were interested in if we can use dust to detect this type of flow, and how we can investigate our physics of acoustic and thermal energy propagating with this flow. And here I have some description of our workflow. To detect the bubbles in the flow, we use actually video camera and run some analysis to estimate bubble velocity, bubble rate, and other parameters. Also on dust side, we mostly use low frequency dust to see how thermal energy propagates, and some additional analysis I will share with you pretty shortly. So this is raw dust data processed only by low passing it below 0.5 Hertz. And what we were doing here, we were injecting some very small amount of hot water to the flow. And here you have a channel. You can treat it as our vertical pipe from bottom to the top, and here at the time of our experiment. And we injection 1 minute of hot water. After that, we let it a bit cool down. Again, injection of hot water in the center, and you see how clearly we can observe it. And I should say that the thermal variations are very, very small. And that's the beauty of dust as a thermal sensor, which we can actually capture with small thermal variations. After that, you can extract the cross correlation between different channels. And what we will be analyzing is the cross correlation peak. It's basically the lag to extract velocity, and some changes in the cross correlation amplitude to extract some thermal dissipation signatures. And of course, even without cross correlation, we can just fit the move out, and using this thermal slugging analysis, we can measure very small velocities such as 0.2 meters per second. And this is the results of our cross correlation analysis. On the left is the lag, or basically we can recalculate it into our velocity. And on the right, it's some thermal dissipation characteristics. It's basically how fast our energy dissipates. And here we have bubble rate you can treat it as a volume of gas in the system. Another thing how you can treat it is a liquid holdup, which is changes. Liquid holdup is a cross-section in your pipe occupied with liquid. So as we introduce some gas, we have less cross-section occupied with liquid. That's why when we added some gas, we have a kind of less effective cross-section and our flow accelerates, so we can capture that. Also, when we introduce some gas, it's brings more turbulence to the flow, and we can capture that the thermal energy dissipates faster. So that's our main observation from this experiment. And another thing we will look in is what's the acoustic signature of the bubbles themselves, of the Taylor bubbles. Again, it's the similar experiment. It's a raw data, it's a low pass by a 0.5 low pass filter. And you can see how even simple filtering amplify some useful signatures in the data. So we can again extract our flow velocities, which is very similar to what we measured with water flow meter. And also you can see some trends here, and this is actually our bubbles. They also create some move out in the data, which is quite visible. And after that, we decided to move to the effects domain. So now we have channel or distance along our pipe on vertical axis and frequency on horizontal axis. And what you can see here that we have some trends like that. What it means that we have some frequency which is was, for example, 80 Hertz when it was close to the bottom of the pipe, and becomes like 60 Hertz when it's propagating. And we can divide this frequency spectrum into several bands and color code it with different colors. And this will be our multispectral plot. And you can do something similar if you have a frequency change in effects domain, you can color code it, and it will provide you with some additional insight. So you extract these RGB values, convert it to RGB image, and for each color you have a different frequency band. And actually it occurs that higher frequencies corresponds to smaller bubbles and lower frequencies to the larger. When the bubble propagates along the pipe, it's due to basically Archimedes forces and other forces which it experiences, it's enlarged. And that's what we see in this data. Initially it was blue, and after that it becomes green. And you have multiple features like that. So that can be used to estimate the size of this Taylor bubble in this slug flow. So for this flow look experiment, those quick conclusions, some established ways, Doppler effect and eddy tracking, but they have their pitfalls. For example, Doppler effect is mostly can be used for airflow, and because you need some differences, some small difference between the speed of sound and the flow velocity. For eddies tracking, it's observed sometimes, but it's still not clear when we observe with eddies, and it could be hardly applied for low-rate producers. So we proposed this new method where you have some thermal variations. You can heat some portions of the well and use this approach to detect not only velocity, but some thermal dissipation features for our particular flow to characterize this two-phase slug flow. And also we propose this multispectral analysis to estimate bubble size. And this also some very useful information for our petroleum engineer colleagues. And my last slide, I guess here I'm just a bit going to the future, how that can be applied in the future. On the left, it's already was applied. It's a paper by Gina et al. So we can use a very similar approach, which I was discussing in real life to track some thermal slugs for oil producers. Other possible applications, there are no any research related to DAS and that, but I just found some nice pictures on that to illustrate. For example, you can put the fiber into some steam flow and try to use it as a Doppler current profiler for some hydrological application. Or regarding these Taylor bubbles, you can find them, for example, as methane bubbles in some seafloor, or even Taylor bubble exist in the volcanoes. So you can listen to these bubbles with dust as a sensitive microphone. With that, I would like to thank RCP, Reservoir Characterization Project sponsors, for their support. And from OpenL side, I would like to thank some funding resources, and also Silixa for providing some very nice guidance on their interrogator. But I open to questions.
Excellent. Great talk, Aleksei. So there've been a number of questions, just a couple here on the bubbles, just sticking for that in the moment as the bubbles are kind of fresh in everyone's brains. How big are the bubbles that you're discussing in these experiments?
So these bubbles are roughly in diameter, it's a diameter of the pipe, so it's 1 inch, and in length it's about 4 centimeters, but they varies, and we can change the size there.
Okay. Can liquid holdup be seen as an equivalent to bubble size?
To some degree, I should say, because if you have a larger bubble size, it means that you have more gas, even with the same bubble rates. You have more gas in the system. So it means that if you have a larger bubble size, it means that you have less liquid holdup.
Great. Returning to kind of the first section of the talk, why did the fiber contract more during cooling than it expanded during heating?
Very good question. So I guess it's probably related to dynamic range issue. So when we heat it up very rapidly, we probably out of a dynamic range. So it's very similar to what I have here. You're basically losing some real signals. But during cooling, it's a very slow process. It takes hours. And that's why we have it gains more strain during cooling period.
Kind of follow up on that. Is the fiber permanently shortened in this process?
In process of cooling?
Is it reversible, this kind of cooling process?
Reversible, yeah. I think while we in elastic range for fibers, it will be reversible. And I think it survives actually pretty, actually I play in the lab, I was trying to put some weight on the fiber and it couldn't survive awesome weight, and it probably could extend like 1 meter. You can extend probably for 5 millimeter. So it's amazing how it's. I'm not sure if it stays in elastic region, but it can survive with extensions.
You think fibers are pre-strained? Are they pre-strained before they're packaged?
For this package, I'm not sure about bare fiber. There could be, I actually found some papers on some pre-straining during processing of fiber. There could be some strain during the process induced there. But I guess for bare fiber, you can treat it as not strained. But for my experiment with stretcher, I pre-strained it because I want to have my input directly from the beginning of my experiment. So when I am applying actually some displacement to my actuator, I want to start straining fiber. So that's something which can deform waveguide a bit. And that's really interesting if someone can follow up on that. It's more like an optoelectronic side of the things.
Yeah. A question from Matt Becker about the kind of temperature, maybe it's also on the photonic side. Have you been able to remove the effect of temperature on low frequency strain by using a calibration bath? So by
actually, for this part, I just detrend it. So during this long time experiment, there was some significant trend in the data where you have just my oscillation kind of overlaid into the major trend. And I approach it just with simple detrending without usage of the BEF experiment. Because again, what I have, for example, for real field cable, this coefficient I have here, it will be different what I have for bare fiber. And even how you put it to the water bath, it will be different. So I guess there should be some better experiments for that. Probably what Matt did with cement, when you cement in cable in place, and you probably can hit somehow more equally the cement, but again, it will be more expansion coefficient of a cement. So you can, that's something interesting to test in the lab. basically these effects.
Yeah, question from Rob about are the fibers in this experiment polymer or polyamide coated?
That's an interesting question. I'm probably not aware about that. I should say that at SMF28 from Corning, the bare fiber was. But for some experiment, I used Luna fibers, which are special sensors, and they actually looks like bare fiber, but they can experience some relatively strong even bending forces. And I think this was polyamide coating, because it's not like transparent, it's with some yellowish color. So I guess this was polyamide, at least for these Luna sensors. For SMF28, I'm not sure. I could check that.
Kind of broadening out a little bit from these experimental results, can you just comment on the applicability of these results to other interrogators? You kind of compared at one point the Luna and the Silixa instrument, but in terms of these other parameters, like
I guess it's something what we need to do as community, because I had this question and I asked OptaSense, I asked Silixa, and there are standards, actually the CFOAM standard, where it could be very useful for comparison interrogators, but I guess I'm still not pretty happy to sharing these full CFOAM characteristics. So I guess we can come up with some stretcher, even with the same methods explaining this CFOAM, and just bring our own interrogators to test them. So I guess most of the results could be applied to other interrogators because they're quite fundamental. Something like this moving average on the fly, I think it's Silixa feature. OptaSense doesn't do that, so you can do it afterwards. So some of them, they kind of interrogator dependent, I should say. But generally, like dynamic range, I also can say about this difference. Is it something from interrogator side? It actually would be nice test just to run the same test with, let's say, OptaSense box, and to see if it's if we still have these changes, so it could deal with some waveguide deformation, or it's something on calibration side. So I guess that's a very good question, and I think we need to move into this direction. And this stretcher is still there. I think Veronica can use it. So just bring interrogator to Lawrence Berkeley lab and test it.
Yeah, great. It looks like Eileen has just copied in
thank you, Eileen.
The document there. John Dwyer asks, would there be a day-night effect in the desert environment?
I guess because as I understand, in desert environment, it's pretty rapid changes. And as we see from Veronica's example, you need to calibrate the temperature pretty, you need to calibrate for temperatures, and it's both temperature of the box, temperature of the cable. But for temperature of the cable, it's a bit easier. It will be observed in all channels, so you can apply just some subtraction of general trend for all channels. For this box changing, if we have some changes in this reference loop, it's something that's something we need to investigate more. But definitely there will be effects, because again, even this parameter, it shows that something like 1 degree Celsius changes, it's more than what it's about 1.4 microstrain. So it's a huge strain applied.
Excellent. Well, thank you very much, Aleksei, and thanks to all our speakers.